Okay, this is another quick introductory video. We'll do work problems later. But so I want to talk about radiative heat transfer. Sometimes you might hear me say in class radiation. So first off, when I say radiation, I don't necessarily mean ionizing radiation like X-rays or gamma rays that have enough energy to remove electrons from your body. That is possible here, but I'm just talking, when I'm talking about radiation, I'm thinking more like a radiator, as in like a hot object that's radiating heat. All right, so, and a lot of that heat ends up coming off in the infrared, not high enough energy to damage yourself. All right, so we're talking about the rate of heat transfer again, so we'll talk about power. So this is power. Units of power are watts or joules per second. Okay. Now, sigma is a constant, the Stefan Boltzmann constant. Making sure I got the spelling right. Yes, it's got two N's, that's right. Okay, and that's just some number. And A is, again, cross-sectional area. E is a thing called the emissivity. It's unitless between 0 and 1. Now, here's an example, right? You could imagine this baseball. What is, sheesh, it's not cross-sectional area. It's surface area. Cross-sectional area was the last one. I should probably just start this video over. Whatever. Am I going to? I don't think so, because I gotta go pick up my kids from school. So this one's going in and it's staying in. My bad. Okay, A is the surface area, right? Not the cross-sectional area. The cross-sectional area is for conduction through a pipe. Okay, we're talking about radiation here, so the entire surface is radiating, not the cross-section. Sorry about that. Okay. So in this case, for example, 4 pi r squared for a spherical object. All right, there goes the ball. Dropped the ball on that one. All right, now, things that are good radiators will have an emissivity close to 1. Things that are bad radiators will have an emissivity close to 0. All right, and so in this case, if something has an emissivity of exactly 1, we call it a black body. Okay, it's a perfect radiator. All right, so enough on that. We'll do worked examples later. I do want you to watch out for one thing, all right? If you imagine me, if you looked at me with an infrared camera, you would see me emitting light, okay? Emitting radiation, okay? Now, I'm also absorbing energy from radiation. Like you imagine if you're let's imagine you're standing outside. You're obviously taking in some energy from the sun while you're also emitting some. And so this is where things get a little bit tricky. You're usually absorbing some power from the environment. So let's say you're in a situation where you're absorbing some energy and also radiating some energy using radiation. In that case, we could say the power from the environment, if it's being radiatively absorbed, would be sigma A E T of the environment to the 4th. And now when you combine these, power net emitted would equal sigma A E, your temperature to the 4th, minus the environment's temperature to the 4th. And just be careful here, right? This is not equal to sigma AE T minus T environment to the fourth. That is not true, right? The fourth powers are on the inside, right? You can't do that. And so what happens is if you're looking at worked examples in textbooks and things like that, a lot of times they'll start with, say, the sun. Okay, and so you have the sun emitting energy into space, and they won't talk about the environment. And you won't see this term in the worked example. Why don't you see that? Well, what's the temperature of space? Pretty close to 0. All right, so 0 Kelvin versus 5,000 Kelvin or something like that. Yeah, so you'll see, or 6,000, whatever it is, 5,800, I think. In any event, a lot of times in space or astronomical problems, you'll ignore this because the temperature of space is negligible, especially once you raise it to the fourth power. We'll do some worked examples. That's enough on that. I better go pick up my